Hey class, we're going to take a look at trigonometric identities. So an identity means that for every value that you choose for x, both sides of the equation come out to the identical result. So for example, no matter what I choose for x here, I'm going to get the same result on the left side of the equals as I get using that value of x on the right side. It's different from an equation because in an equation you solve and you find certain values of x will make it true, but not every value of x. An identity, every possible value of x makes both sides equal. Here's some identities that we've already talked about. We can build the tangent of theta from the sine of theta divided by the cosine of theta. And then cotangent, we just flip those. And this is just based on stuff that we've learned already. Reciprocal identities we've looked at. Pythagorean identities we've talked about, and you can shuffle them to make different identities from the existing ones. Even odd, remember the cosine is even, so the cosine of negative theta equals the cosine of theta, whereas the odd functions, the sine of negative theta is equivalent to the negative sine of theta. Okay, and then from these Pythagorean identities, we're able to change what's on each side of the equation and create new ones. So I know from this one here that the sine squared of theta would be equal to 1 minus the cosine squared of theta. And here's some more that can be built from these Pythagorean identities. Okay, and how do we simplify the trig expressions? Well, typically we're going to rewrite an expression in terms of sine and cosine only. We may want to multiply the numerator and denominator by a well-chosen one in order to move it into a different form, more simplified form. And we might want to write sums that are ratios as a single ratio. And we might use some factoring. So we'll tear into all of this as we do examples. So we'll start with this right here. So the cotangent divided by the cosecant of theta. Our goal is to rewrite it using just sine and cosine. Okay, so on this first example, we want to rewrite it in terms of sine and cosine only. And so the cotangent, the identity was that is equal to the cosine over the sine. Okay, so that's the cotangent. And then below that, we've got the cosecant. And the cosecant is going to be 1 over the sine of theta. And if I flip these and multiply them, I've got the cosine theta times the sine of theta over the sine of theta. And then the sine of theta divides into itself. And it leaves us with cosine of theta. So what we've established is that the cotangent of theta over the cosecant of theta is an identity with the cosine of theta. Okay, so let's look at this part B here. It's actually asking us to multiply the numerator and the denominator by 1 minus sine theta, because that's going to help us take this and move it into this and show that those are identities. So we're starting with a cosine of theta over 1 plus sine of theta. And we're going to multiply it by 1 minus sine of theta over 1 minus sine of theta. Okay, so this is just a well-chosen one, and we can multiply anything by 1, and it retains its identity. So we're not changing it. We're just looking at it in a different way. On top, we're going to get cosine theta, and I'm going to leave that factored out, times the 1 minus the sine of theta. And then remember that this is a factored form of a difference of squares, right? If I take an a plus b times an a minus b, it equals a squared minus b squared. Okay, so this is going to be like 1 squared minus sine squared theta. And this piece here, the 1 minus sine squared theta, since we know that sine squared theta plus cosine squared theta equals 1 from our Pythagorean identities, I could subtract sine squared theta from both sides, right? And that would tell me that the cosine squared of theta is equivalent to 1 minus the sine squared theta, exactly what we've got here. So I'm going to rewrite this as a cosine theta times 1 minus sine theta over a cosine squared theta. And then one of these is going to divide out in the denominator, and this one's going to divide into a 1. So I'm going to reduce this to just a cosine theta. Okay, and so we've ended up with 1 minus sine theta over cosine theta. And we've shown that there's an identity relation between this first we started with and what we were able to move it into using the identities. Okay, for this next example, we're going to try and rewrite this with a common denominator, and then we're going to simplify it so that it's only in terms of sine and cosine. All right, so if I'm going to get a common denominator, then I would need to multiply the top and the bottom of this first rational expression by the cosine u. Okay, and then missing from the denominator here is the factor sine u, so I'm going to multiply this second one by the sine u on the top and the bottom. Okay, so now we know we've got a common denominator of sine u times cosine u. And I'm going to take this cosine u here and distribute it across here. So I end up with cosine u. Okay, the cosine u times 1 plus cosine u times sine u. I'll go ahead and write that as sine u times cosine u. Okay, and then this part, I'm going to distribute the sine u across these two here. Okay, so I'm going to distribute this part. Let me give myself some more room here if I can. Okay, so that's going to be another sine u, but it's going to be cotangent u times sine u. And minus sine u cosine u. Okay, both of these are now over the common denominator we built of sine u cosine u. Okay, so if I put all of this over the common denominator, let's see what happens. Okay, so the payoff here is going to be that I've got a plus sine u cosine u and a minus sine u cosine u. So this term is going to be subtracted out. And I've got cosine u plus cotangent u sine u over sine u cosine u. Okay, now not everything is written in terms of sine and cosine yet, but I know that the cotangent we can write as the cotangent is going to be the cosine of u over the sine of u. And then that's times sine of u. Okay, and that helps me because this sine u divides into itself as well. And all I've got left here is the cosine u plus cosine u. So I'll write that as 2 cosine u over sine u cosine u. Okay, and now I can divide the cosine u factor into itself, and I end up with 2 over sine u. Okay, for this last example D, it asks us to factor this. So I can think of this as a difference of squares, a squared minus b squared. And then I can see that I've got a common factor of the tangent of v here. So if we factor that as requested, we're going to get a sine v plus 1 times a sine v minus 1. Factoring out the tangent, we get a tangent of v times sine of v minus 1. Okay, now I've got a common factor on the top and bottom of sine v minus 1. So this would be sine v plus 1 over tangent of v. And we really can't do anything with it past that. Okay, so for this example, we're going to be using the reciprocal identities. And we're just going to take this original left-hand side and derive the right-hand side by applying identities. So we've got a cosecant of theta times a tangent of theta. And we can rewrite the cosecant of theta as 1 over the sine of theta. And we can rewrite the tangent, of course, as sine theta over cosine theta. And then the sine divides into itself, leaving us with 1 over cosine theta, which has a reciprocal identity, secant theta. Okay, so we brought this side to that side, applying identities, and we've established that this is an identity for secant of theta. Okay, for this example, we're going to use a little bit of our even odd identities. So we start out with the sine squared of negative theta plus the cosine squared of negative theta. And we want to show that that is equal to 1. Okay, so let's start by saying that what we really mean by a sine squared theta is a sine, or in this case, negative theta. So we're just going to rewrite this, and it's okay, so in that form. So because of the odd identity, we can take this negative out here and write that as just sine of theta squared. And then, of course, the even identity says the cosine of negative theta is equivalent to the cosine of theta. And now, when I square this, it's like a -1 times the sine of theta. And I'm squaring the -1, which becomes a +1. So this just becomes the sine of theta squared. Okay, and remember this is equivalent to a sine squared theta plus a cosine squared theta if we write it in the trigonometric form that we are used to seeing. And by the Pythagorean identity, that is equal to 1. Okay, in this next example, we're going to do some similar things as in the last example, but we're going to take and show that this is an identity, and we'll derive the right-hand side to show that each side of this will be the same value for every value of theta that we plug in. So it's worth a lot to us here to simplify something that's this complicated and whittle it down to a very same result for every theta that's much less complicated. Okay, so I'm going to start by doing what we did last time and just bring that negative out front and write it as squared, and then it's a minus this time. Okay, so the odd brings the negative out front. The the even property means the negative can go away because it's the same. Okay. And then down here, we're going to use both those properties again. So I'm going to bring the negative out in front of the sign. And then we're subtracting. And the cosine negative theta is equivalent to the cosine theta. Okay, now up on top here, we square that -1 in front away. So we can write this as a sine square theta minus, I lost my theta. So sine squared theta minus cosine squared theta. And that's going to be above here. And I'm going to factor a negative out. And that way I can write this as sine theta plus cosine theta. Okay, because on top here, what we have is a difference of squares, a squared minus b squared. So I can write that as sine theta plus cosine theta times sine theta minus cosine theta. All right, and then down here, I've got this -1 times sine theta plus cosine theta. And then I've got a common factor, this sine theta plus cosine theta. We'll divide into itself. Leaves me only with a -1 down below. So it's like I've got a sine theta minus cosine theta up here and a -1 down here. So if I distribute that -1, I can bring the cosine in front. Negative cosine will make that positive cosine. And then we're going to negate the sine. And we've brought this side to this side. So that was our goal. Okay, so with this next example, just want to illustrate that there's sometimes more than one way to get to there from here. And in this case, we want to get to tangent u from 1 plus tangent u over 1 plus cotangent u. And I'm going to do it like this. I'm going to think of the 1. So I know that the tangent u here is going to be the sine u over the cosine u. Okay, so that's my tangent u. And I have to add 1 to it, and I want to make a common denominator, so I'll think of my 1 as a cosine u divided by itself. And then that gives me a common denominator to bring those together on. So I'm going to do that same thing down here. And I know that the cotangent of u is going to be the cosine u over the sine u. Okay, so I'll need to think of this one to get a common denominator as the sine u over itself. Okay, so I get a complex fraction, and on top I have a cosine u plus sine u over cosine u. Down here I have a sine u plus cosine u. Over the common denominator of sine u. Okay, so this is going to pay off here when I flip and multiply. So I'm going to end up with a cosine u plus sine u times the sine u. All right, so that brings up here and multiplies. And then this cosine u is going to be multiplied by this on the bottom. So I've got a cosine u times a sine u plus a cosine u. Okay, and so what I have in common here is this cosine u plus sine u. Addition is commutative, so I could think of both of them as sine u plus cosine u and divide that into itself. Leaves me with a sine u over a cosine u, which is otherwise known as the tangent. Yeah. So we got there from here. Okay, this next one's going to take a little bit more time. So obviously we want to start with this and derive this. So let's start with the sine theta over 1 plus cosine theta. And we're going to bring these two rationals together with a common denominator. So of course I'm going to need to multiply the top and the bottom of this by the sine theta, right? That's what it's missing. And we're going to take that plus 1 plus the cosine of theta over the sine of theta. And then it's missing the 1 plus cosine. So we'll multiply the top and the bottom by that. Okay, so when we bring this together on the top, we're going to get a sine squared theta, and then plus 1 plus the cosine theta squared. So remember, if you take a plus b squared, you get a squared plus 2ab plus b squared. So this is like a and this is like b. So that's going to turn out to be 1 squared plus 2 times 1 times cosine theta plus cosine squared theta. Okay, so I multiplied that, got the sine squared. The product of 1 plus cosine theta times itself is the rest of this. And then on the bottom, I've got the common denominator of a sine theta times the 1 plus cosine theta. Okay, now I'm going to bring the sine squared theta and the cosine squared theta together on top. Okay, because we should be recognizing that as a 1, right? Plus 1 plus 2 cosine theta. Okay, so this just makes a 1. And that 1 plus the other 1 is going to be 2 plus 2 cosine theta. I'm going to factor the 2 out. That'll be 1 plus cosine theta. That's also what I have down here. Okay, so we'll get to divide that into itself, and that leaves us with 2 over sine theta. But sine theta has a reciprocal relationship with the cosecant. So the 2 over sine theta is equivalent to the 2 times the cosecant theta. Okay, so right-hand side is derived. Okay, for this example, I want to start by rewriting everything in terms of sine and cosine. So this is what we start with, the tangent v plus cotangent v on top and a secant v times cosecant v on the bottom. So we're going to rewrite the tangent v as sine v over cosine v. And for the cotangent v, we're going to rewrite it as cosine v over sine v. Down here, secant v is going to be 1 over cosine v times cosecant v, which is 1 over sine v. All right, and then on top, I'm going to rewrite it with a single common denominator. So I'll have to multiply the left by a sine v over sine v and the right by a cosine v over cosine v. So we end up with sine v over cosine v times sine v over sine v. And then here I get cosine v over sine v times the cosine v over cosine v. Now down here, this just works out to 1 over cosine v times sine v. Okay, so when I take this on top, I end up with a sine squared v plus a cosine squared v over the common denominator we created of cosine v sine v. Down here, I've got 1 over cosine v sine v. Okay, so flipping to multiply, I'm going to come down here. I'm going to end up with a sine square v plus cosine square v over cosine v sine v, and then times cosine v sine v over 1. And then these divide out, and we end up with sine square v plus cosine square v. And the Pythagorean identity tells us that that's a 1. Okay, on this example, I'm going to take this left side to the right-hand side, and I can see that I want somehow a 1 plus sine theta in the denominator. So that's what I'm going to introduce here and try and create the denominator. So I've got 1 minus sine theta over cosine theta. And I'm going to multiply that by 1 plus sine theta over 1 plus sine theta. Okay, and where will that take me? All right, so this is a factored difference of squares of 1 squared minus sine squared theta. So I'm going to rewrite that as 1 squared, which is just 1, minus sine squared theta. And then here I've got cosine theta times 1 plus sine theta. Okay, and if I rework the Pythagorean identity, I can think of the cosine squared theta as 1 minus the sine squared theta. I'll just substitute that. All right, and then one of these on top is going to cancel or divide this will divide into one of these two factors. So this will just become cosine theta. So we end up with what they asked for here, cosine theta over 1 plus sine theta. Okay, and this last slide indicates some of the guidelines that we've established here. You always want to start with the more complicated expression and create the simplified expression, unless they're if they look about the same complication to you, then you can't do that, of course. But and it just gives you some pointers here is which identities you want to tap into to help you move one towards the other and prove that these are identities.